My name is Sree Harshini Satheeskumar, and my project is a comparative study of LSTM and T5-Flan models for automated test case generation from Gherkin requirements. And in the Polygence research program, I did this project under the mentorship of Mohit Manohar. So, test case generation. It's a crucial step in a software's testing process, and it's often traditionally a manual and time-consuming process, which is prone to human error due to things like inconsistencies or overlooked scenarios. Therefore, automated test case generation using AI models has gained prominence in this field lately, and it offers substantial benefits in terms of efficiency and reliability. So, understanding the comparative strengths of different models in this domain is helpful for optimizing software testing practices. My study specifically compares the effectiveness of just two AI models, which is the LSTM or Long Short Term Memory Network and the T5-Flan. So, it should be noted, however, that the study does not gauge or adjust the model's potential for comprehensive test case coverage. Rather, it gauges the effectiveness of each model in capturing the essence of the requirements and producing clear and relevant test cases for a limited number of scenarios, positive and negative. And by concentrating on the quality and relevance of a few key test cases, we aim to provide basic insights into the practical application of these models into automated test case generation for larger and more comprehensive requirements. Oh, sorry. So LSTM networks are a type of recurrent neural network, also called RNNs, designed to handle sequential data by learning long-term dependencies. They are particularly effective for sequence prediction problems because they have this great ability to retain information over extended sequences. This makes them suitable for tasks involving time series data, speech recognition, or in our case, text generation for test case generation. Yeah. On the other hand, the T5-Flan model is a transformer-based architecture model that excels in processing and generating text by leveraging a more advanced architecture. Transformers, unlike traditional RNNs like our LSTM, use attention mechanisms which capture dependencies and semantic relationships across entire input sequences, which allows them to handle larger contexts and generate more coherent and or contextually accurate outputs. Now, for this study, we compare and analyze the performance of these two models in terms of accuracy, efficiency, using a diverse dataset of Gherkin scenarios and evaluation metrics. The evaluation metrics, which are BLUE, Rogue, BERT score, and semantic similarity. BLUE, or bilingual evaluation understudy, measures the precision of n-grams, or exact sequences, in the generated text compared to a reference text. So kind of like comparing the answer key to the answer, evaluating how closely the output matches the reference in terms of word sequences. Rogue, or recall-oriented understudy for just primarily measures the recall of n-grams, which basically compares the overlap of word sequences, checking for text coverage rather than exact alignment like BLUE does. So BERT score, third one, uses a pre-trained BERT embeddings to evaluate semantic similarity between generated and reference text cases. So this one focuses on meaning rather than exact word metrics, unlike BLUE does. And semantic similarity, our final one, quantifies how closely the meaning of the generated text aligns with the reference text by comparing the semantic content rather than just word overlap, so similar to BERT score. Our results. So, based on the average scores of the evaluation metrics on a unique set of a unique test set of requirements, the T5 model was found to outperform the LSTM across all metrics. It shows higher scores in all the BLUE, Rogue, semantic similarity, BERT score, and yeah, that's it. Therefore, if we consider these metrics as indicators of performance, then the T5 model demonstrated superior performance compared to the LSTM for generating test cases for the given tasks. So, if we analyze our results, The LSTM's poorer performance might be attributed to the fact that recurrent neural networks, which is what an LSTM is, require large and diverse datasets to effectively learn patterns. Our dataset consisted of about 600 to 700 unique test cases, but even this might not be enough. So this might have limited the LSTM's ability to generalize to new test cases and perform better in the accuracy metrics on a new set. Um, Additionally, the LSTMs often struggle with modeling complex relationships and long-term dependencies, which are crucial for generating coherent and accurate test cases, unlike the T5, which already has that ability. The relatively small dataset size could have also led to this thing called overfitting, despite precautions added like dropout layers. In contrast, modern transformer-based models like the T5-Flan have attention mechanisms, as I said before, that better capture dependencies and semantic relationships, making them more effective for tasks like generating test cases, which require at least a good, deep contextual understanding of and semantic relationship understanding. Making them more effective for tasks like test case generation. Okay. So, in conclusion, while the LSTM has its limitations, it offers a foundational approach that could be improved on with more data and advanced architectures. So further research could, in this field, or for this project, could involve refining these models by integrating things like maybe domain-specific knowledge or exploring hybrid approaches that leverage the strengths of both LSTM and transformer-based architectures. Thank you.